Two blocks of masses 2 kilograms and zero point 0.5 kilograms are attached at the two ends of a compressed spring. The elastic potential energy stored in the spring is 10 joules. Find the velocities of the blocks if the spring delivers its energy to the blocks when released. We have already solved a similar problem before, and if you have time you can watch that one because the first part of this problem will be very much similar to that one. So here is the situation that we have a spring and it is compressed. There are two masses attached to this spring. So one is m1, another is m2, and because I am pushing these two masses from both sides, the spring will be compressed. So I stop at certain compression level. So here where the problem starts. They say that when I am compressing the spring and I just stop somewhere, the blocks are at rest. So at that time their velocity is v1 equals 0 and v2 equals 0, because I am not pushing it further and I am not releasing my force, so they will stay where they are and a spring will be compressed at that time. So their initial velocities are at that time the velocities are 0. Then next I release these forces which I am applying. So I release these forces. So what will happen? I have a simple animation to show you the nature of this motion. So you can watch that and then we will come back to solve this question. I also included this animation in the previous similar example. So if you have already seen that, you can simply fast forward to the solution of this question. So here I have an animation. It may not look very natural, but I hope it will make you understand the motion. So here is the spring which is compressed between two masses m1 and m2. So just imagine that there are two forces from right and left which is pushing the masses towards the spring. So spring is now compressed. At this time, Vi1 is the velocity of mass m1, Vi2 is the velocity of mass m2, and of course these two velocities are 0 at this time because they are at rest. So now just imagine that I will remove forces from right and left which is stopping them to go away right now. So I am removing those forces and let's see what will happen to the motion. So the motion will go like this. The spring will expand, masses will go away from each other, and they will arrive at certain maximum displacement, and then they will come towards each other. And then once again the spring will be compressed, and because of the compression it will expand, and because of the expansion it will compress. So a motion like this will go on indefinitely. It will never stop in our situation because we are ignoring frictional forces and the spring is ideal. There is no dissipation of energy, so a motion will remain like that. And the final velocities, you can see vf1 is the final velocity of mass m1, vf2 is the final velocity of mass m2, and then we will calculate the ratio of these two velocities. Okay, so now you know what was happening as a result of removal of the forces from the sides. So I told you before that whenever you have such a situation in which masses are involved or a system is involved and then something happens to the system and then suddenly the situation changes, an event occurs, so you can always use the law of conservation of momentum to solve the problems, and especially when there are masses and velocities are involved. So if masses and velocities are involved, there is a system, then something happens, and then a state of the system changes. So you can always use the law of conservation of momentum and law of conservation of kinetic energy if needed. So let's use the law of conservation of momentum first because it's simple. So let me write down the data. So I assume m1 equals 2 kg and m2 mass 2 is 0.5 kg. Initial velocity is v1 before the event. Similarly for mass m2, v2 is the velocity before the event. Then we assume that v1 prime is the velocity after I release the forces from the sides. Similarly, we can call it v2 prime is the force after the event. This data is very important. Next, we will apply the law of conservation of momentum, and it's very simple, so I will not talk much about that. So the initial momentum is, there is no half because the momentum is mass times velocity. So momentum of the mass m1 is m1 v1. I will add the momentum of the second mass is m2 v2, and this is total mass the total momentum of the system before the event, and it should be equal to the total momentum of the system after the event when I will release my forces from the sides. So the momentum of the first mass after the event is m1 v1 prime. Similarly, I will add the momentum of second mass. It should be m2 v2 prime. It was given in the question that two blocks of masses attach at the two ends of a compressed spring. So if the spring was compressed, it means the two masses were at rest and their initial velocities, for example, initial velocities mean the velocity of the masses before the removal of the forces, they should be equal to 0. So v1 and v2 velocities of the masses before the removal of the forces, they are 0. So if they are 0, this term will become 0, this v2 will become 0, and this whole side will become 0. So I can write it like that. Okay, so one more thing I am forgetting, that if we assume when two masses are attached with the spring, so in this case when they are in compression it's okay, and when I will release them they will go away from each other, and as a result the spring will expand, and because of that expansion they will come closer to each other. So in both cases, suppose this is mass m1, this is mass m2, so this is velocity v1 and this is velocity v2. So throughout the motion of this system, velocity v1 and v2, they will always be directed opposite to each other. So just assume that velocity v1 and v2, they are always opposite to each other, and we already know this fact. So we can incorporate this information into the equation anytime you want. We will just place a negative sign because this is very customary to place a negative sign if you want to show that direction of something is opposite to some other quantity. So we always place a negative sign. So we already know this information, but if you want to incorporate this information, you can add it here or you can add it at the very end of the solution. So if you want to add it, for example, so you can add a negative sign here. If you assume that motion to the, if direction of the velocity is towards the left, we will take it as negative. If direction of the velocity is towards the right, we will take it positive. So according to this notation, you can place a negative sign here, or you can, we already know this information, you can add this information at the very end of the solution if you want. It's just a matter of direction. So this should be equal to negative m1 v1 prime plus m2 v2 prime. and I can bring one side to the left because I don't like this negative sign with this term, so it will become m1 v1 prime equals m2 v2 prime, and then I can write it like these are, I can v1 prime equals m2 over m1 v2 prime. And if you remember our previous question, we actually found the ratio of v1 prime and v2 prime, because I can take v2 prime on this side and it will become a ratio, and we have already done that. So the problem was when we found the ratio of v1 prime and v2 prime, because we did not have enough information to find the exact values of v1 and v2 prime. That's why in the previous example which I solved, we only stopped where we found v1 prime over v2 prime, because with one equation we can't get the exact values, because the number of unknown are 2 and we have only one equation. I can give you an example for that. For example, I tell you that a plus b equals 9. So can you tell me the values of a and b? You can tell me that we can't get the exact answer to your equation because there are many solutions. For example, I can say that a could be 7 and b could be 2, because their sum is 9, right? 7, 8 and 9. 7 plus 2 equals 9. So this is also a solution to this equation. I can also say that maybe 5 plus 4, mean a is 5 and b is 4, and we know 5 plus 4 equals 9. I can also say maybe the solution is 4 plus 5. A is now 4 and b is 5. That is also a solution. So there could be many solutions to this problem. If I want to get an exact answer, which I already have in my mind, I need to give you another equation which is different than this one. For example, I give you that okay, a plus b equals 9, and then I give you another equation that a minus b equals 3. So now the number of unknowns are 2, right? One is a and another is b, and I want you to tell me the exact values of a and b. So because the number of unknowns are 2, I need to give you two different equations. So now you have two equations, so you can find the exact answer to my question. For example, you can solve them. I can just add them up, they will cancel out. It's 2a equals 9 plus 3, 9, 10, 11, 12, and then a equals 6. So now you can tell me, okay sir, we found the exact value of a, it is 6. Okay, now tell me the value of b. It's easy, you can just use any one of these equations to find the value of b. Let's take the negative the equation with the negative sign. So a minus b equals 3. If a equals 6, it should be 6 minus b equals 3, and b equals is actually negative b, 3 minus 6, and if I solve it further, b equals 3. Okay, so now you can tell me that we have found the exact solution to your problem, because their number of unknowns were 2 and I gave you two equations, so you can exactly find the solution. It is actually 6 and 3. A is 6 and b is 3, and if you add them up, its answer is 9. And if you subtract a minus b, it's equal to 3. 6 minus 3 equals 3. So this is the exact solution. Although these solutions are also right, but they are not the exact solutions. I mean the solution I had in my mind. So if the number of unknowns are 2, you must have at least two equations, two different distinct equations to solve or to find the exact values of each variable in the equation.
So, the conclusion of this discussion is that in this situation, when we use the law of conservation of momentum, we have this equation, right? We have m1 is constant, m2 is constant, so we don't have to worry about that. But v1 prime, velocity of the mass m1 after the event, and then velocity of mass 2 after the forces are removed. So these two, there are two variables and we have only one equation, so we cannot find exact values of v1 prime and v2 prime. So we have to express them in terms of the other. For example, I have written v1 prime in terms of v2 prime. This is not the right exact solution, because I told you, when you have two unknowns, there could be many solutions. So how can we find the exact solution to this problem? I mean, they told us to find the velocities. If you go to the question, find the velocities of the blocks. So they told us to find the exact velocities, not like v1 prime equals something m2 over m1 v2 prime. No, no, no. We need to find the exact value, whatever it is, v1 prime and v2 prime. So how can we do that? So the you can conclude from my discussion that we should have at least another equation with which involves these two variables, but it is a different relationship. Then we can solve to find the exact value. So how can we get that second equation? The clue should be in the question. So let's see. The elastic potential energy stored in the spring is 10 joules, because the spring was compressed because of the forces from the left and right sides on the masses towards the spring. So the spring was compressed, and you know, when a spring is compressed, energy is stored inside the spring. So when I will remove the forces, that energy is released and masses will move left and right. The first they will go away from each other and then they will come to each other. So this motion will go on. So energy, so the key word is energy. It means I can use the law of conservation of energy, because the total amount of energy which was stored in the spring is given, it's 10 joules. So let's go to use the law of conservation of energy, and hopefully we will get another equation, and then we can find the exact values of v1 prime and v2 prime, mean the velocities of the masses after the forces are. Okay, so let's mark this equation as equation A, because just in case we need it, we can take its name. So the law of conservation of energy, what is that? The law of conservation of energy for an isolated or closed system, it says that total energy of the system remains constant. So whatever is the total energy, it will always remain constant no matter whatever happens to the system, whether it is compressed or whether it is released, or whether it is in the middle of somewhere, whether maybe it's half compressed and half in motion, whatever. Total energy should be constant. And now we need to find what is total energy. So that total energy is kinetic energy, because it is in motion, plus potential energy, and it is constant. It should remain constant no matter whatever happens to the system. So it says, for example, when the spring was compressed, totally compressed initially, there was total 100% potential energy and kinetic energy was 0, because the blocks were at rest. We already assumed at the beginning that velocity v1 and v2, they were 0 at the in beginning. And when it was released, so this energy, potential energy, will decrease and it will convert to the kinetic energy. So slowly the kinetic energy will increase and potential energy will. So as the potential energy is losing, the kinetic energy is gaining that energy. For example, at some instant, potential energy is left with 80%, then kinetic energy will have 20% of the loss of potential energy. Similarly, when the spring reaches at the equilibrium, potential energy will be only 0% and kinetic energy will be 100%. And when the blocks moves further away from the equilibrium, then once again potential energy will increase and kinetic energy will lose, and when they reaches at the extreme points, mean at the maximum displacement, potential energy will be once again 100% and kinetic energy will be 0% at that time. So no matter whatever happens, this sum will always be equal to 10 joules, because it is given in the question that the total elastic potential energy of the spring is 10 joules. So it will be 10 joules. So whatever happens, whether one increases or other decreases, their sum will always be equal to 10 joules. So now, as we have seen that when the potential energy, for example, at some point, potential energy was lost 20%, so that was the gain for the kinetic energy. So I can write an equation that the gain in the kinetic energy is equal to the loss of potential or loss in the potential energy, because at somewhere when the potential energy was lost 20% here, so that was actually the gain in the kinetic energy. So I can assume, for example, when a spring reaches at the equilibrium, then kinetic energy was 100% and potential energy was 0%. So I can assume that case that the gain in kinetic energy is equal to the total, when the masses are at the equilibrium, then I can say that the gain in kinetic energy is equal to the total loss of potential energy. So I can write that equation here. So the total kinetic energy will be the kinetic energy of mass m1 and kinetic energy of the mass m2. Of course, that is the total kinetic energy of the system. So I can write that in mathematical form as half m1 v1 prime squared plus half m2 v2 prime squared. The kinetic energy of mass m1, kinetic energy of mass m2, and it is equal to the total loss of potential energy. So that is the total elastic potential energy, and it is equal to 10 joules. So now I got my second equation, and because these are two simultaneous equations, mean they are true at the same time, so I can solve them together. So here is half m1 v1 prime squared plus half m2 v2 prime squared, and I name it as equation B. So now I will solve these two simultaneous equations. The first one is A, which I got from the law of conservation of momentum, and I have already isolated v1 prime, and it is equal to m2 over m1 v2 prime. So I will plug this value into equation B, which I got from the law of conservation of energy, and then I can find the value of V2 prime. So before that, let me get rid of these two in the denominators because I don't like them. So first I multiply this whole equation with 2, and I know these two on the left side will vanish, and it will become m1 v1 prime squared plus m2 v2 prime squared is equal to, now this 10 will be multiplied with 2, it will become 20 joules. And now I will plug in the value of v1 prime. So just remember that I have the value of v1 prime, and it is v1 prime squared. So I will write it m1 and then I will put the square first, and then I will write the value of v1 prime, which I got from the law of conservation of momentum, and it is m2 over m1 v2 prime. So it is m2 over m1 v2 prime plus m2 v2 prime squared equal to 20. So let's simplify it. m1, so if I take the square of all of these terms, m2 squared over m1 squared v2 prime squared plus m2 v2 prime squared equal to 20 joules. So now this m1 will cancel out with 1m, so I can write it as m2 squared over m1. Just remember, it is now not squared because 1m1 is cancelled with the outside m1. v2 prime squared plus m2 v2 prime squared equals 20 joules. So once again I will take v2 prime squared as common, so v2 prime squared is common. It is m2 squared over m1 plus m2 equals 20 joules. So because I will isolate v2 prime squared, let me make it in a compact form so that I can easily m1, so it is m2 squared plus it will become m1 m2. If you know a basic algebra, you know how am I doing. So now I want to get rid of this term with v2 prime squared, so I will just multiply both sides with the inverse of this term. So v2 prime squared equals, this term will cancel out, and here I will get on the right side the square, the inverse form of this expression. So m2 squared plus m1 m2, and it will be multiplied with 20 joules. Okay, so I got the final expression for v2 prime squared, and I need to insert the values for m1 and m2. So let's find the values. What is m1 and m2? So I will go to my data, and okay, so m1 is 2 kg and m2 is 0.5 kg. So let's plug in these values to get the exact value of v2 prime. Let me write the values here. m1 is 2 kg and m2 is 0.5 kg, just in case I won't forget the values. So I am writing the values. m1 it's 2 kg, m2 squared mean 0.5 kg squared, and then plus m1 is 2 kg, m2 is 0.5 kg, and multiplied by 20 joules. And my calculator tells me that v2 prime squared equal to 32 meter squared per second squared. And because we are looking for the value of v2 prime, not in the squared, so we have to square root the answer, and it's equal to 5.66 meter per second, and this is the value of v2 prime. We have just found it. So now next step is easy. We can find the value of v1 prime easily just by putting the value of v2 prime, because if we put the value of v2 prime here and we already know the mass m2 and m1, we will just get the v1 prime value. So let me write v1 prime. So v1 prime equals m2 over m1 multiplied by v2 prime, and I know the masses m1 is 2 kg and m2 is 0.5 kg, so 0.5 kg over 2 kg multiplied by the v2 prime velocity 5.66 meter per second. And the answer to this question is, and my calculator is giving me the value of 1.42 meter per second. So we have found the values for v1 prime, and this is the final answer to your question. So I just want to point out one thing about the direction, because these are the velocities, so we need to give the direction of these velocities, because velocity has a direction, right? So we know that what is the direction of the velocities, but let me reiterate again so that you understand. The direction of v1 prime, because when the spring is compressed, they are at rest, and then I release these forces from the sides, and then the blocks will move away from each other, and after they reach at the maximum displacement or the maximum distance from each other, they will come towards each other. In any case, or at any instant, the direction of velocity, suppose this is v2 prime and this is v1 prime, their directions are always opposite. So whenever is happening, their directions are always opposite. Even when they are coming closer to each other, their directions are opposite. So for that, and also remember that their directions will change, because when the spring is expanding, the v2 is towards the right and v1 prime is towards the left, and when the spring is compressing, the direction of v2 prime is now towards the left and direction of v1 prime is towards the right. So their directions are always changing, but they will remain opposite at every time. So now if you insist for the negative sign convention, because when we put a negative sign with one and positive with the other, it shows that they are always opposite. So you can put a negative sign with any one of them. So you can put v2 prime, a negative sign with v2 prime, or you can put a negative sign with v1 prime, which will always show that the directions are opposite. And the putting this negative sign with anyone, it depends on your reference. Suppose you want to assume that if the direction is towards the right is positive and direction towards the left is negative, or maybe someone else may say that no, if the direction towards the left is positive and if direction of the velocity is towards the right is negative, it depends. So you can just put a negative sign with anyone, maybe just v2 prime. So just put a negative sign and you are all set. Or alternatively, you already know, so you can just write this description at the very end to give the information about the direction, because velocity is a vector quantity and you are supposed to give the information about the direction of that quantity because you have given the quantity. So you can just write this description at the very end of the answer, or you can put a negative sign with any one of them just to show them that they are always opposite.